Cochlear Model. In normal hearing, sound travels from the outer ear through the middle ear to the cochlea, where it converts into electric impulse that the brain can understand. Most cases with severe hearing loss involve damage to the conversion of a sound and electric impulse in the cochlea. A cochlear implant bypasses this natural conversion process by directed stimulation the auditory nerve with electric pulse. Hence, the cochlear implant will have to mimic and replay auditory function from the external ear to the inner ear. Block diagram for key components in a typical cochlear implant system. The implants contain another coil that receives the radio frequency signal and also hermetically seals electronic circuits. The circuits decode the signals, convert them into electric current and send them along wires threaded into the cochlea. The electrodes at the end of the wire stimulate the auditory nerve connected to the central nervous system, where the electrical impulses are interpreted as sound. Filters. The schematic diagram of the continuous interlevel sampling reprocessing is similar to the complex analog processors, but the band-specific signal is subject to envelope extraction via either rectifiant low-pass filter with scope of frequencies typical, set at a range of 160 to 320 Hz. The lowly varying temporal envelope from 3 to 4 spectral bands can deliver high levels of speech intelligible in quiet. Block diagram for the continuous interlevel sampling cochlear implant speech processor, which is similar to the complex analog processors. The envelope is complex to match the narrow dynamic range in electric simulation, and the envelope from each subband is then amplitude modulated to a pulsatil carrier that interleaves with pulsatil carrier from other subbands. To avoid electrode interaction caused by electrical fire overlap in simulation with conceivable can smear the band spinor, cause the envelope from each subband in the amplitude modulated to high rates, 800 Hz, pulsatil carrier that interleaves with pulsatil carrier from the other subbands. In other words, only one electrode is being stimulated at any given time. A representative intracochlear array for cochlear implants. The white rings on the black carrier represent electrode contacts, which stunts stimulate the nerve auditory neurons in the modules. Electrode interaction. Schematic representation of how two interacting electrodes can reduce the number of independent neural of functional channels, which are represented by an array of arrows. The upper panel shows a case of two totally independent electrodes, with each stimulating an independent neuronal canal via relatively small degree of electrical field spread. Change in electrical dynamic range caused by electrode interaction. Open symbols represent original T and M levels measured for individual electrodes in isolation. Solid symbols represent modified T and M levels measured using live speech as a calibration signal. Let us begin with a formal mathematical definition of the temporal envelope and fine structure, and then proceed with examples to illustrate their meanings. The formal definition is based on the Hilbert transform method, that different from the Fourier transform that separates a complex signal into low and high frequency components, divides a signal into a slowly varying and a rapidly varying component for a real signal and analytic signal.